Alright, looks like we're live. Hello everyone and welcome to yet another recreational programming session. So let's make a little bit of an announcement and officially start the stream. So let me see, what are we doing today? Red Circle live on Twitch. And what are we doing live on Twitch? That's a very interesting question. Let me copy paste the topic. Today we're implementing function pointers. So should have actually fixed that. So let's give the link to the Twitch channel, twitch.tv/Sodding, and let's ping everyone who's interested in being pinged, and the stream has officially started. Hello everyone, welcome. How are you guys doing today? Hello Catalin the Cutie, hello Crossity Nerd, hello MM2PL, welcome, Vincent Hawks, hello Small Clover, hello, welcome. So we continue developing our programming language called Porth. It's I'm sorry, I just hit my microphone stand. I should be a little bit more careful. So we continue to program our programming language called Porth, which is basically stack-based programming language. You can find the source code of this thing in here. If you're watching on YouTube, you can find it in the description. And if you're watching live, you can find this thing in the chat. I just copy-pasted it in the chat. So essentially, what is a function pointer? Right, so if you programmed in C, you probably know what it is. And if you are coming from the functional programming world, you would say that it's basically a lame implementation of functions as the first-class citizen, whatever is that supposed to mean, okay? Essentially, let me actually demonstrate what that means. You have some functions, so this is going to be C. I'm going to demonstrate this thing in C. Right, so here is that. We're going to return this stuff like this, and I'm gonna say hello world, right? I'm gonna say hello world, and maybe I also want to put a new line in here, and then I'm going to compile this entire thing, and I'm gonna just run it, and it should say hello world. Okay, it says hello world. Let's define a couple of functions, right? Let's define function foo, right? And let's define function bar. And both of the functions, let's make them produce some sort of side effects, right? So the first function will produce side effect called foo, and the second one will produce side effect called bar. And if you call them in sequence, you would see something like foo bar, right? So essentially in C, you can take a pointer to a function, right? So in fact, according to C, it would be nice to put void in here, right? Because according to C standard, if I remember correctly, the function defined without any arguments is kind of considered a variadic function. Right, it's sort of considered something like this implicitly. So I can even demonstrate you that. So I can just do something like this, and I think it will compile. I'm not 100% sure, but it does. As you can see, it does in fact compile, and I'm gonna sneeze to celebrate that. Just a second. Debated. So yeah, as you can see, the function that doesn't accept any arguments and doesn't define void in here is considered variadic, not polymorphic, variadic function. So to ensure that you can't pass any arguments in there, you have to put void. But this is specifically a C thing. In C++, you don't have to do that, right? So if you just basically compile that with C++, so let's put something like this, and I'm gonna do G++ instead. It's going to complain anyway. So this is sort of like a small, less known semantical differences between C and C++, right? So I'm just explaining why I'm putting void in there. So I think we've got a couple of subs, actually one sub. Kavantix, thank you so much for 2 months of tier 1 subscription. Thank you, and welcome to our epic Porth club. Welcome. Really appreciate that. Okay, so here we have two functions, and you can take pointers to those functions. So let's actually go in here, and I'm gonna try to do something like this. So, and a pointer to a function, usually people define a type def to represent the type of the pointer to a function, right? You can do it like this. So this is going to be void, and I think, let's call it something like func, And there we go. So that defines a new type, which is the pointer to a function with this specific signature, exactly the signatures of bar and foo. So then you can define an array of such functions. You can define something like funcs, right, and you can put foo and bar in there. Right, there we go. So, and if I understand correctly, this should just compile, and as you can see, it does in fact compile. And then we can go ahead and iterate through these functions and call them. Right, so let me try to do that. So I'm going to define n, which is the size of this array. So if I take the size of this array, it gives me the size in the bytes. So to get the size in elements, I have to divide it by the size of one single element. And then we're going to iterate through this entire thing and do something like this. Right, and then we just do funcs I and just call this function. And if I try to call that, it still produces the same side effect foo bar, but since it's an array now, I in fact can actually have several elements. Right, so I can do something like foo, then bar bar, and they're going to be called like in that specific order, as you can see. So we have only two functions, but we have an array of pointers, right? And then we're iterating through that array of pointers and we're calling these functions. And that sort of creates something that OOP people would call a polymorphism. Right. So, and this is quite useful for this kind of situation, right? All of the sort of like religion aside about pure functional programming and first-class citizen, you know, functions and, you know, weird claims about maintainability of that approach, like all of that aside, function pointers are very useful for writing this kind of code, right? For writing this kind of code. And especially they're extremely useful for compressing huge switch cases or switch if-elses. Right, in our compiler we have a lot of if-elses, so these ones are quite easy to implement, I think. You just define an array, but for the behavioral switch cases, I think we can find them somewhere in the generator. Right, so as you can see, depending on a type of operation that we're compiling, we have to generate different assembly code. Right, what we can do, we can put each an individual sort of generator into its own function and create an array of function pointers where an index is the number of the instruction. So instead of doing a huge switch case, we can just iterate through instructions and use their IDs as the index in that array to quickly look up the behavior in O of 1 and then just call it, which will dramatically speed up the entire process because here we have to do O of n lookup. Right, and the reason why I implemented it like that is because I originally implemented it like that in Python, and the reason why I originally implemented it like that in Python because I knew I'm going to be re-implementing it in Port where I don't have function pointers. You see what I'm talking about? So now we come to the point where we want to implement function pointers, and the implementing function pointers will allow us to compress this entire behavior. So basically I want to build some sort of a table where at this specific index we're going to have a function that generates just this assembly code, and that way we'll be able to compress like a lot of these huge if-elses in the compiler. That's basically the idea of today's stream. Does it make any sense? Oh, we have a lot of subs in here. So, hey GVT, thank you so much for tier 1 subscription. Thank you, really appreciate it. Actually gifting to Sergey Larinov. Welcome, Sergey Larinov, to our Epic Port Club. Defense, thank you so much for 16 months of tier 1 subscription. And Hamikovi, thank you so much for 21 months of tier 1 subscription. Almost 2 years. Amazing. Thank you. So, all right, does anyone have any questions about what I just explained? Does it make sense why I want to implement function pointers for Port? Taxborn, thank you so much for Twitch Prime subscription. Thank you, thank you, thank you. All right, so looks like no questions regarding this specific feature. Right, so, and the question is how we're gonna implement that in Porth, right? So I already demonstrated how it's going to look like in C, right? So how it looks like in C, not how it's gonna look like. It's already implemented in C a long time ago, in fact. So this is how people usually do that in C, but Porth has a slightly different syntax and semantic from C, so we cannot just like straight up copy this idea. We have to come up with something. We have to come up with something. Melitap, thank you so much for 4 months of tier 1 subscription. Thank you, thank you, thank you. So, okay. Here is an idea. We're going to probably introduce a couple of special keywords, right? So if I go to main, maybe I'm gonna actually create like a separate file, foo.porth, and I'm gonna just do std.porth, and then we have to define an entry point because we recently implemented, so you can't have a Porth program without an entry point. And then I'm gonna have something like foo, and in foo I'm going to call foo puts, right? So let's actually put some sort of like a new line in here. And if you write foo, what's gonna happen is that it's just gonna call that function. That's it. So let me try to do that. I'm gonna do porth, compile, run foo.porth. And as you can see, it just like called foo. So we need to be able to push an address of foo to the data stack. Right. So for that we need some sort of a special keyword. So the specific keyword doesn't really matter, right? So we're gonna go and just define something like address of, right? So this is a special keyword which basically, and since it's a keyword, it's not like introduces any runtime thing. What it does, it looks into the next token. And if the next token is a word that is associated with a procedure, it will take its address and push that address onto the stack, right? So on the top of the stack, you're gonna have the address of this foo instruction. Okay, then you want to be able to call that procedure, right? So, and I think we can introduce yet another keyword that just calls the address at the top of the stack, right? Sounds good? Sounds pretty good. Another interesting thing is that our language is statically typed. And that's where we have, you know, a little bit of a problem. So what if this function accepts a couple of integers, right, and returns a single integer? So, and to facilitate that, I'm going to just drop one integer and I'm going to let the other integer to fall through. So how do we know, like, the signature of this entire thing? So essentially we need to extend the type system so it supports the, you know, contracts of the functions that, you know, we push in there. Which is quite of a rabbit hole, to be fair, right? So it's not like something that I can easily implement within a single stream, right? So not only I have to implement, like, you know, take an address, calling the functions and stuff like that, but also I need to, like, implement a lot of like new structures that facilitate storing the signatures in the type stack and stuff like that. So one of the ideas I had is essentially, what if I provide the type signature in the call itself? What if the call, in fact, is going to be some sort of a block, right? So essentially, I'm going to say call it like this thing accepts 2 integers and returns 1 integer, right? And the language is going to just use these contracts to type check everything. But that, well, that is a little bit easier to implement, right? That is a little bit easier to implement. Still, it's kind of hard, right? So I probably need to store this entire thing somewhere, right? So I need to allocate like a new array of contracts of call instructions. You know what I mean? Like I need to store this thing somewhere, and it's like not particularly easy to implement. So I think I know a pretty easy hack, right? So this kind of contract is already stored somewhere. it's already stored in the definition of the procedure foo. Right, so if I have several of such functions like foo and bar, right, can I just go ahead and create the keywords called call like foo, and it's going to call the address on the top of the data stack, but it's going to use foo for type checking. So basically, whatever you have at the top of the stack, call that, but call it like you would call foo. Don't call foo, just call it like you would call foo. Basically, use the contract of foo to type check the data stack, because usually when you do polymorphism, all of the functions have the same signature, right? They accept the same arguments, and they accept and they return the same arguments, right? So the only thing you need to definition of a one function, right? And basically this entire thing is going to just look up the contract of this thing and use that contract in type checking of this specific line. So yeah, it's kind of crappy, it's kind of meh, but it gets the job done. You see what I'm talking about? Right, and it requires introducing only two keywords, like address of that thing and call like that thing. So, and that way I think it's doable within a single stream, if you know what I mean. So I think I could implement these two keywords within a single stream, and it's actually kind of cool. So we'll use dummy functions as type definitions. We don't have to use dummy functions. We can literally use one of the functions that are in the table of functions that we're using, right? So we probably know one of them, so we can just use that one. It's not necessarily has to be a dummy one. It could be a real one. It's not going to be called. It's just used for type checking. But if you call a function with the wrong signature, it would compile, but it fail at runtime. Yes, it will. I really like this. The function already has to be defined somewhere. It makes it easier to change the signature of the function. That's actually an interesting way to look at it. There is some sort of the idea in here that waits to be explored for sure. So let's try to implement that and see. Maybe we're gonna discover something interesting. So you could use an empty-ish proc as kind of type def for call like. You could, but I already discussed that. You don't have to. You can use one of the like production functions that you put in the table for as a template. So why not? It's not implemented yet, by the way. So. So ideally, I would like to have a type system that just stores the contract on the data stack, on the type stack, not the data stack, but type stack, right? Ideally, I would like just have address of. It would literally take the contract of this thing, right? Well, maybe I kind of can associate that. No, I cannot. Especially if it's going to be stored in the memory, it's not going to work like that. Yeah, it's definitely not going to work like that. So yeah, ideally I would like it to like associate the contract and put it into the data, into the type stack, and then I could do call, and call just looks at the type stack. But again, it will take too much time to implement within a single stream, so I'm not going to do that. Allowing to cast functions to different signatures is so wildly unsafe, I don't even think it's worth implementing, to be honest. You're phrasing it like you need to put some work into allowing unsafe casting of functions. But the reality doesn't work like that. In fact, you have to put more work to disallow casting functions to different types. It's not how it works, I'm really sorry. It is easier to write a language where you can reinterpret functions however you want, right? It's not how it works, I'm sorry. Alright, so I guess we want to start. Let me actually make a small break because I didn't pour a cup of water before the stream, and it's kind of difficult for me to, you know, to stream without water. So it's going to be super quick. All right, let's go ahead and try to implement this entire thing. So by the way, I think it's quite important to actually introduce a separate type for the procedures. We need to introduce the separate type for the procedures. So right now, the type system has only 3 types. So we have integers for just, you know, integer stuff, Boolean for conditions, and pointers for pointing to a memory to read the data and to write the data. So for the pointers to the functions, I would like to have a completely separate type, right? So you don't accidentally call integer, Boolean, or pointer, right? So, and you can only call that specific type. And I think since I already called this thing an address, I might as well call the type address, right? You have pointers, which is the like pointer to a data, and address is the pointer to the procedure, right? So there's like a difference between, you know, an address of data and address of code. So, and you can only call a thing that is an address, right? So the first thing I would like to do, I would like to introduce a new type. So let's take a look. Porth.porth. All right, and let's see where the types are defined. Data type. So here are the types. So we have integer, pointer, and Boolean. Let's go ahead and just introduce the ADDR, and there we go. So it's aligned perfectly the first time. And let's try to recompile the entire thing. Okay, so we're gonna start going through all of the assertions and just like add all of these things. So basically this function takes the name of the type and converts it to like its ID, right? So it's usually used for parsing and stuff like that. So this is ADDR and this one is ADDR. Cool. Next, please. So it's the other way around. So it takes the ID and converts it to a name. So this could be replaced with some sort of an array, but I don't think this function is called that often, like for that to matter. So yeah, I'm gonna keep it like that. So ADDR, and let's take this entire thing. All right. And oh yeah, this one is rather interesting. So for each individual type, we have a separate instruction in the intermediate representation. Right, and which is not particularly ideal, right, but it is like that right now, right, it is like that right now. So in the future, I'm thinking that maybe I'm gonna collapse all of the push instructions into a single one and store the type of that instruction in the operand. Unfortunately, instructions right now have only one single operand, but this is already the second time I'm thinking about introducing the second operand to the instruction, which is probably something that I want to do. All right, so if like the code kind of demands to introduce more and more things, maybe at some point we just have to do that. We'll see, we'll see. Okay, so we have that. Now we have a new instruction which actually increments the amount of ops we can have, which triggers like a lot of more asserts that I have to update in the entire code base, right? So you see sort of like a compiler assisted refactoring. The compiler assisted refactoring is sort of already possible with Porth, right? With the compile time asserts and stuff like that. Okay, so the next one, yeah, there we go. So we incremented the amount of operations. Now we have to update these things as well. Cool. So this is the pointer and this is an address. Okay. Next one. Okay, so now we're talking about generation. So, and this is the reason why I would like to compress all of these pushes, push integer, push boolean, and push pointer, because when I'm generating an actual assembly out of them, the assembly doesn't give a shit, right? For the CPU, all of those things are just numbers, right? So the CPU doesn't distinguish between integers, booleans, pointers, addresses, it's just like fucking numbers, right? And because of that, we have to generate the same shit in here, but once we compress all of that, maybe it's not gonna matter anymore. We'll see, we'll see. So we're gonna implement everything eventually, right? First, we need to get the shit done. You can't get the shit done if you don't get the shit done. I don't know what I'm talking about. Okay, so I probably need to increment this assertion, right? And the next assertion is going to be here. So what do we have in here? I think this is compilation, right? And the compilation when we encounter a word, right? The compilation when we encounter a word. And why do we want to care about different kinds of operations in here? I'm not quite sure. I'm not quite sure because I think I know why. Because a new operation may introduce a new code in here. Yeah. I see. I see. So essentially, if we introduce a new operation, maybe there's some sort of a word associated with this, but I don't quite remember. I don't think this thing is introduced as anything, so I'm gonna just like leave it as it is. I'm not 100% sure. I'm not 100% sure. Okay, so here we have 3 types. So this is the constants, right? So this is about the constants, because in the constants, it's actually rather interesting. You can define constants. Foo. Let's actually do something like foo 5. And if you do... Let's remove this thing. I'm not sure if I want to remove it, because I'm going to be using that for testing in the future. So it's kind of dangerous for me to remove that. If you do something like foo, it is going to have a type of integer, because the number literals have type integer by default. So I think I need to sip my water. And so you'll be able to, I suppose, add something in here. And if you try to run the entire thing, it will work as usual. But you can always cast this entire stuff into the pointer. And when you use this constant, the type of the constant is going to be a pointer, right? So constant kind of remembers the type of the last element on the stack when it was computing that. So, and as you can see, it cannot compile that. So this thing is about that, right? So we encounter a constant, and if the element after calculating the constant is, and if the type of the constant is that particular type, we have to use the corresponding instruction here, right? So that means we'll be able to do things like cast ADDR. I think we'll be able to do this kind of stuff, yes. Which is rather interesting. So yeah, you'll be able to just take a number and cast it to address, which is something that you probably shouldn't do, but if you need to, you can do that. Anyway, so do data type address equal, then drop OP push address. There we go. So here we're basically converting the type into push, which is rather interesting. Maybe I should extract that into a separate procedure. So, and that procedure is going to accept the data type and just return the push instruction. That sounds something interesting, yeah. Lindra Braga, thank you so much for 14 months of Twitch Prime subscription. Thank you, and welcome to our Epic Porth Club. Thank you. All right. So, yeah, I should probably go in here and just do it like that. Let's try to compile the rest of the stuff. Okay, so in here, we have a type checking, finally. Okay, this one is interesting. So, when we encounter type pointer plus integer OP push address, right? We're essentially pushing the address thing on top of the type stack, right? So I have to do something like ADDR, right? So now this entire thing participating in the type checking, hopefully. We'll see how it goes. And of course I forgot to increment this entire thing, right? And it kind of compiled, but at the same time, it kind of didn't work, and I'm not sure why, because I forgot to put equals in here. Yes, of course. Thank you so much. Thank you. And looks like we just introduced a new type. Believe it or not, we just added a new type to the type system of Porth. Isn't that cool? I think it's pretty cool. x8664, right? And I can just like recompile this entire thing one more time. And yeah, so on top of having like booleans, integers, and pointers, we now have addresses. We can try to test that. So I'm gonna go to foo.port, but maybe first I want to move the output to port, right? Yeah, it doesn't be like be like that. So foo port, as already said, you can just do addr, and theoretically this should already compile. I think this should already compile, but I don't remember the compiler prompting me to add a cast addr. I don't remember it prompting me that. So maybe this is something that we'll have to fix in the future. That's actually very important. So I'm gonna try to go and port compile foo, and it will tell us that, yeah, so unsupported word. So, all right, let me go into the compiler and let me find OP push integers. So on top of these things, I think it's somewhere in intrinsics. Yeah, because cast is an intrinsic. Where are the intrinsics? Here they are. And here are the cast, and we don't have an assert in here. That's right. So essentially I forgot to put assert in here for the amount of types. So we can do assert exhaustive exhaustive cast intrinsic. Do I spell that correctly? Intrinsic definition exhaustive cast intrinsic definition. Okay, so I think that's fine. Count data types, I'm gonna say that we're expecting 3, but in reality we have 4 of them. Right, I need to recompile the entire compiler, and as you can see, count. Oh, and count data types is actually defined below. All right, this one is interesting. Okay, so that means we'll have to move that sort of module, right? So I sort of like outline the modules with like begin and end in here, because like port does not support modules yet, but in the future it's going to support them. Right, so this is that, and I think this thing should be defined somewhere here, so otherwise it cannot see that. All right, so as you can see, so this thing is triggered, and we'll have to introduce cast addr, which will trigger more errors because that changed the amount of intrinsics we have, right? Okay, static assertion, there we go. So now it prompts me to add, you know, the name for the intrinsic and so on and so forth. So, Fabulous Flo, thank you so much for 4 months of Twitch Prime subscription. Thank you, and welcome to our Epic Port Club. Thank you. All right, so this thing has been updated. We're gonna have like 45 intrinsics. My god, that's a lot of intrinsics. So in the future, maybe we're gonna compress some of this stuff, but for now it's fine. Some of these intrinsics are not going to be available on all of the platforms, right? In WASM, I'm pretty sure you won't be able to have that. And to be fair, in WASM, it doesn't make sense to have even syscalls, right? Because there's no really syscalls in WASM. You have external functions, but external functions are very much variable. So, I don't know. Maybe we're not going to have that. We'll see. The winner gets T, that's for sure. Okay, next one. So this is basically the parsing, right? We're mapping the name to a specific ID, which is quite important. So addr. So, and this is generation, and in case of a generation, it like doesn't matter yet again. So maybe this thing should not be an intrinsic, but I don't know. Okay, and in here, oh yeah, I already actually did that. So what else do we have in here? Type checking. Okay, so type checking is actually kind of important. This one is actually very cool. Yeah, that is very cool. So I have a function called expect arity, right? And essentially it checks whether there is at least like this amount of elements on the type stack, right? And it returns those elements, so you can use them back in the type checking. So essentially, it doesn't really matter what this entire thing means. You can simply copy-paste this entire stuff for now and replace it with ADDR. So basically, this is how cast works. Maybe I should actually factor this out into a separate function to implement different casts, so I don't repeat this kind of stuff too much, but I don't have time for that. So we're gonna do that later. You can always do that later because it's super easy. I usually tend to not focus on things that are too easy to refactor, that you can do that later, right? So obviously this thing is easy to refactor, so you can just like, you know, bulk refactor it later. It doesn't matter. So what's important is to have like a proper new type in the compiler. That's what's important right now. So cast integer, I think I forgot to, oh yeah, it was complaining that I forgot to increment this, I think, okay. And I think we've done that. So we finally have a proper new type, all right? And I can even cast to that type. I won't be able to do anything with that type, but I can cast to it, which is nice, I think. So full port, there we go. Intrinsic cast is not supported in compile time evaluation. Okay, so this is something that we probably also need to add support for, right? So let's actually find this entire thing in here. And so where is the cast boolean? So cast pointer, cast, all right. So in here I can also copy paste that. So it's gonna be just like maybe ADDR. Do I want to add an assert in here? Do I want to add an assert in here? I'm not sure. So you see how we copy pasting like type related casting and type related stuff quite a lot, which means that it should be generalized somehow, but I don't really know how, so I'm not going to do that yet, right? So I just need to add more types so the patterns are more visible, if you know what I mean. Right, so the patterns are there, but they're not that super visible. Okay, so now we're having something. Look. Argument 1 of plus is expected to be type integer, but got type address, right? So our compiler can like knows about type address, right? So it says the argument 1 provided here, right? So here's the argument 1, but the expected type was provided in here because plus is an intrinsic, so it just points in here. So we have an address. We can't call it yet, but yeah, you can just like take anything and cast this thing to an address. Isn't that amazing? I don't know, maybe. So looks like it needs another assert. I'm not sure if it really needs another assert in there, because it feels like, so there's a lot of copy paste in here, which leads me to believe that maybe all of that has to be compressed somehow. So the casting is definitely has to have some sort of a second operand. Yeah, here's the thing. Intrinsic is wrapped in an operation, right? So let me show you. Intrinsic is wrapped into an operation. So we have a struct, let me see, struct operation, and then you have OP type, right? OP type, type, something like this. And then you have some sort of an operand, right? And essentially an intrinsic is OP with the type OP intrinsic, and specific intrinsic being intrinsic cast integer or something. So because of such definition, the intrinsics can't have their own operands because the intrinsic itself is an operand, right? So which is another case of this structure wanting to have actually two operands, right? So it feels like one operand is just like not enough. So it would make sense to have actually two of them. So that way I could actually have like an intrinsic cast, and the operand of that intrinsic would be something like data type, you know, pointer, right? And that is a specific cast to which you're casting. So in that way, maybe you will be able to eliminate the need for that assert in the future, but all of that is in the future, right? So for now, it probably makes sense to add that assert in there. But yeah, we'll see. And the question is, how many operands do we want to even have in there? How many operands is sufficient? It depends. It depends on what we're doing, right? 1 is not enough. We want to have 2, but what if in the future 2 is not going to be enough, right? Do we want to have 3, 4? How many do we want to have? Or maybe we should have just 1 operand, and that operand has to be a pointer to a bigger structure? I don't know. It's kind of like there's a lot of like freedom in here on how you can organize this entire stuff. It's just like, yeah. Just looking at the chat, is there anything related to what I'm doing? Looks like that's it. Looks like this is the only questions that are related to what I'm doing right now. Okay. So yeah, I think it makes sense to add another assert in here. So assert. I keep saying that pretty much every time, at like almost every stream, maybe, but quite often that I think people are too scared of copy-pasted code to the point that it's counterproductive. Copy-pasted code is actually very useful because, first of all, it lets you get shit done very quickly. Second of all, it reveals the patterns that require abstracting out, right? So essentially, quite often people try to develop things top-down, basically first come up with the abstractions and then fill in the abstractions and implement them. And quite often they do that incorrectly. They quite often come up with completely incorrect and wrong abstractions that don't solve anything, and they have to tear them down and start over. So if you go the other way around, you just like implement without any abstractions, just copy-paste. Copy-pasted code helps you to reveal the patterns that needs to be abstracted out. So you let the code do the abstraction work for you. See what I mean? So, and that is a very useful instrument that a lot of people are scared of, right? People straight up scared of duplicate code because they're scared that people are gonna laugh at them, that they're bad programmers. In fact, like if you know how to use copy pasting as a tool in writing better code, it's actually very, very valuable. It's extremely valuable because it allows you to explore the space of the problem a little bit better, and then you will see how to abstract things out. Does it make any sense? Maybe it doesn't. I don't know. So yeah, I don't know where it's coming from. I think maybe from universities, or maybe from the principles of don't repeat yourself, the biggest sin that you can have. I don't know. Okay, exhaustive handling of casts in, where are we? In eval const value. Exhaustive handling of casts in eval const value, and we're gonna do count data types, and this is gonna be something like for equal and. So pointer, boolean, and also we don't support integers, so maybe we want to add an integer in here because why not? Maybe this is something that you'll be want to be able to do. Okay. So let's recompile the compiler. Okay, so everything seems to be compiled. And if I try to run that, so what do we have in here? I can always cast this entire thing back into an integer and just bring that. So everything seems to be okie dokie karaoke. So maybe the first thing I want to do, I want to basically commit whatever we have, right? So commit the fact that we added the address type. So introduce type ADDR, and I'm gonna push that right into the repo, mate. Right into the repo. Right. Okay, so that's cool. I suppose the next thing we want to be able to do, we want to be able to do address of. We have the type address. Now we need to be able to legitimately get the value of such type. So, and I suppose the time has come to introduce the keyword address of. So before we can go ahead and implement that word, I think we need to add the editor support for that word, right? Let's actually start with the editor so it highlights that word so we can easily see that. Pierre Reem, thank you so much for Twitch Prime subscription. Thank you, thank you, thank you, and welcome to our Epic Porth Club. How about it? Alrighty. So I'm gonna go into the editor folder, and I'm gonna start with Emacs because I primarily use Emacs, and then second one is gonna be Vim. Maybe I'm gonna start separating things into several lines, right? So this one is ADDR off, right? So then I'm gonna go into Emacs, emacs.local, and this is where I'm going to copy paste this entire thing. Okay, so I'm gonna restart my Emacs. I just realized that something's weird going on. Did I close my terminal? I think I just straight up closed my terminal for whatever freaking reason. All right, didn't mean to do that. So Porth, and let me open this thing. There we go. So now we have address of, and in a Vim we want to do a similar thing. Do I have a highlighting for Vim script? I'm not really sure, so maybe I should probably do that in Vim. Porth.vim, and here are the keywords. ADDR off. So here is the keyword. Now I'm going to go to Porth and find the keywords. So we have a list of all of the keywords in here. Let's add another one, keyword ADDR off. And again, that should trigger a chain reaction of different asserts in all of the places. And hopefully if we make changes in all of these places, we're gonna have a new keyword. We'll see how it goes. So Porth compile, porth.porth, there we go. So yeah, this one is pretty important. ADDR off. ADDR off. And of course I forgot to update to 18. Emacs is too slow. Like, it's like reacts slower than I type. It's just like really infuriating. Okay, so ADDR off. ADDR off, and then if I go here, maybe something with my keyword. Handling keywords. Do I want to handle a keyword in there? Actually, maybe. Who said I cannot handle that keyword? So I think it's actually a very interesting idea to be able to do const foo, right? ADDR off foo, and that's a constant that holds the address of foo. I didn't see anything wrong with that, and then I can do something like foo and call like bar. Why not? Sounds good to me, I think. I think it sounds good to me. Right. Oh, Gia, hello. What's up? How's it going? How's it going? All right. So let me see. So we support keyword and keyword offset, keyword reset, and the next thing we want to support is keyword address of. And if we encounter something like this, we have to get the next token, right? So we need to get the next token. And how do we get the next token? We do that through the Lexa, right? So we do that through the Lexa. I will be learning Rust this semester. Nice. So you're gonna know what's this all hype about. But you already know Rust as far as I know. You researched Rust for your language, I think. And on top of that, you can actually do like a almost pure FP intellectual masturbation in that language, so it shouldn't be that bad. So you can program it just like in Haskell, almost. I don't know. So you can always have fun with the Rust, right? If the Rust keeping you hostage, you can always find a way to, you know, to have fun, I think. All right, so let's take the next token and go back in here. Right, so though I'm not quite sure. So this is the Lexa. And I did a little bit of a fucky-wucky because I left my Lexa on the stack. Right, I left my Lexa on the stack and I just like work with it like that. So I'm not quite sure if right now on the stack I even have anything. Right, so maybe here there's like literally nothing. Maybe there's literally nothing in there. So there's a bunch of assertions and okay, so in here probably I want to do 18 because otherwise it's not going to properly do that. There we go. So here is the integer and here is the pointer, and pointer is the Lexa. Okay, so luckily if I do over I will get the Lexa still, right? So I'm actually quite lucky in here. So that means I can do things like, well, not really, because like I have an extra type in there. Have an extra type, because in here is a completely different situation, right? So you have a pointer, then you push a token, and then I should have actually saved the Lexa on the local memory. So this is probably something that I want to do. Right, this is definitely something that I want to do. And it shouldn't be that hard, I mean, right. So let's go ahead and do that. So this is going to be memory, Lexa, and I'm going to keep the pointer to the Lexa, so because I'm going to be modifying that Lexa. So then I'm going to just save this entire thing in here. Right, so here is the Lexa, and instead of over, I'm going to be doing like Lexa pointer, and there we go. So yeah. So all of that is needed because like working with the stack and return stack, working with the data stack and return stack actually kind of sucks in Porth, but I have a couple of interesting ideas on how to improve that a little bit later, maybe on the next stream. We'll see. We'll see. The winner gets a T, that's for sure. Trust me, I'm a professional software engineer. Okay, so let me try to compile this entire thing. And in here, I just have an integer, and that integer is the keyword, specific keyword. So Lexa next token, I can now do something like this. Right. So if I remember correctly, the thing essentially returns Boolean, and if it returns false, that means there is no keyword after, there is no thing after the address of. So we'll have to throw some sort of error. Oh, and it's interesting, if Lexa next token returns false, token is not modified, so it will point to the previous token anyway. Token location pointer plus, and I want to print that specific location, right? So we're going to have an error, and in an error we have to say expected procedure name after keyword address, keyword name, but found nothing, but got nothing. And then I'm gonna exit with 1. And also let's align input. There we go. So here's the location, expected procedure after this keyword, the keyword. Cool. Now the next thing we have to check, if the token type is not equal to token word, right, we'll also have to say something. So it's gonna be 7. Now error expected a word after This one is rather interesting actually, because we can use the human, yeah, we can use the human token type. Expected, right, something like this, where I would say token word, human type, and also I have to use human singular, human token type, right? Expected this thing after keyword, and we can say what that keyword is after this keyword, but got another inputs, and in here we'll have to say the type that we've got. We have to say the type that we've got. We can even sort of like do the following thing, form this stuff. So token dupe, and then inputs, and then exit, and then we're gonna drop in here. Right, that forms a block. And now I should be able to align by input. And I can clearly see that I forgot to put inputs in here, in all of these places. And in that place as well. Okay, so here's location expected token type after keyword that. We might as well actually wrap all of that in here. But got something else, right? But got something else. Got that thing. So this is basically the checks that we have to perform or throw some sort of errors, and we'll probably have to duplicate that code in some other places in the compilation specifically. So maybe we'll have to extract that to a separate separate function. We'll see about that. We'll see about that. All right, so what do we have? Not enough arguments for the drop, which is kind of sus, not gonna lie. So what are we supposed to have in here? So we have integer type. Huh. What are you talking about? Not enough for the drop. Oh, I suppose... Is that because... I don't know why. So what exactly we're dropping in here? This is kind of interesting. So here is the token, right? Did I accidentally consume that thing? I didn't think so. I actually didn't think so. Oh, maybe I'll have to drop it somewhere. I don't know, man. Like, what the fuck? We're not consuming anything in here, so everything seems to be fine in here. Why would it be a problem? So let me see. Not enough arguments for the drop. Not enough arguments for the drop. So, oh, I know what. Because we were dropping the Lexa that I moved into the return address. Okay, so now we don't have to drop anything. And it has nothing to do with that stuff. Alright, that is actually very cool. So that means I can uncomment the entire thing in here, right? And finally type check it. And it seems to be type checking, so which is fine. Alright, so, but it's not fully implemented yet, right? So let's do something like this. To do ADDR off, compilation is not fully implemented yet, and this is going to be more of a like this. So inputs, this is another inputs, and then we're going to do exit with non-zero exit code. So this is not going to fail, but let's compile with FASM Linux x86-64. And then I want to move output.porth. Okay, so, and then I can compile full.porth. Yeah, so it's not fully implemented. It would be also nice to have the location of this entire thing, I think. Right, so I'm going to take the token location pointer plus, and I'm going to say located here. Right, it's a special word that takes a location and just formats a special thing, right, that is useful to use. Okay, so maybe I'm going to do it like that, where I'm going to try to compile the full.porth, like so. Yeah, there we go. I can do that with a single line. And this entire thing is located in here, right? So Cool. So we only need to implement this entire stuff. How are we going to be implementing this entire stuff? Since it's a word, I think we need to get its value, right? We need to get its value and look up the procedure with that value, right? So let's go ahead and do that. So maybe I want to make a small break. I think I want to make a cup of tea, right? So because I'm running out of steam a little bit. So let's make a small break, and after a small break, we're going to continue implementing this entire thing. All right, so I have my tea, and let's continue. So what do we have in here? I already checked for this entire thing. So I suppose now I need to take token value. And I don't remember, for words, how do you interpret them? Do you interpret value as a string, or do you interpret it as the as an integer? So I think for string literals, it is a number in a string literal buffer, but for the words, it is literally a string that refers to the original file string, because we basically memory map files, and then some of the tokens like refer into that memory that, you know, was mapped. So let me see, we can always actually check it out. Token word. So, and let's find all the places. Oh yeah, there we go. That's kind of interesting. Yeah, so we literally interpret it as a str. So if you take a look at the token value, you would see that you can interpret token value both as integer and as a string. So token value is more of a union. And we are implementing unions in here in a very interesting way. So essentially, through an offset, you can define the size of the field, right? You can define the size of the fields. Here, what we do, we take the size of the integer and size of the string, and we're finding the maximum between them. And that's the size of the field, and that's the way we implement unions, right? It's an interesting hack. It actually fits perfectly with the hack of offset reset that is both used for defining structure offsets and the enumerations, right? We use the same mechanism for both enumerations and the structures. And unions are just like, it's like a single max, and that's literally the reason why I did that intrinsically here, so we can do something like that. So, and depending on the token type, you can interpret token value as either integer or a string. So that's pretty cool. All right. And in here, I can just do something like this, str, right? So I have to do pointer plus, I have to take the token pointer, offset it to get the pointer to the field, and then read the string out of that field, right? And then we have a function, something like proc, maybe look up, look up proc by name. And this entire thing returns a pointer. I'm going to duplicate it and compare it to null, because if it's null, that means this thing does not exist. If it's pointer equal, we'll have to throw an error. Okay. That's kind of weird, but okay. So what we're going to say in here is error procedure that... and we'll have to take, probably, we can actually kind of duplicate that stuff, can we? I don't think we can. Right, we'll have to do that one more time. Though I can do this stuff, I can duplicate this thing, like so, right? And then form yet another block in here. Right, so here I have a pointer to the value, right? I have a pointer to the value, I duplicate it and read it and then look it up. So in here at the top, I just have a pointer, so I can do something like over str and just eputs and then say does not exist. And that's it, I think. I think that is literally it. And then I'm going to exit with non-zero exit code, and here I can align eput. So something like this. So I push this entire thing here, and I sort of form a block where at the top I have that. Then I use this thing in here to look it up. And if this entire thing is null, this is how we operate in here, and then we dropped everything in here. But if it's not equal null, we'll have to do something else in here. We'll have to take the address, right? But we'll see. Okay, first I'm gonna go here and I'm gonna try to grab something that doesn't exist. Address of buzz. And let's try to compile the entire thing. Okay, the compiler is compiling. Procedure buzz does not exist. Perfect. So that's precisely what I expected. But if I go in here and say foo, it will say a different thing. It will say that address is not fully implemented. Okay, so that means it fell through this entire thing, right? It managed to find such procedure and it fell through and it said that this thing is not implemented yet. Perfect. So, and this is probably somewhere here. We have to take an address of the procedure. So here at the top we have the procedure and I'm going to duplicate this entire thing. Proc address pointer plus, right? And I can read it as an integer, so this is the point, this is basically the procedure address. And we need to, I don't even know what we need to do in here. I think we need to push it into the stack. I think that's what we have to do in here. We have to push it onto the stack. And the type that we have to use in here has to be the address. Right, there we go. Though we can do something like this, right? So it has to be over, right? So we use this type, we use this value, and we push it into the const stack, right? And I think that that is the entire implementation, basically, if I understand it correctly. Hopefully I do. So, and hopefully I'll be able to factor out all of this code to reuse in actual compilation, because this is just compile time evaluation of our nation. But yeah, we'll see. Okay, so let me try to recompile this entire stuff. Unknown word call like. Okay, so that's cool. So we don't have such thing yet, but we can try to, for instance, I don't know, cast this entire thing to integer and print it. This is something we can do. And that way we know the sort of like an internal address of this entire thing. Or do we? Oh shit, we don't. Yeah, we don't. This is not really like an address of the procedure. This is the index of the operation where procedure starts. But I would expect the actual address in there. That means we have to go into the generation, into the code generation. Generate OP Intel and Pro. Okay, so remember how I said that this entire thing is going to be the same for all of the types? This is not true for the address. This is absolutely not true for the address. Because in case of an address, we actually want to push the label address. Because whatever we have in an operand is just like the index for that thing. Right. That's what we want to do actually. So that's the difference. You see, this is why I try to copy paste first, because at the first sight, it looks like it's compressible, but then you start developing further and no, not really. It's like that specific little thing has to be slightly different and you keep copy pasting it, right? So it's just like, it's not always right? You just have to keep copy pasting until the pattern like emerges that you can actually like compress. This pattern is not particularly compressible yet, though we're getting there. We'll see. Okay, so I'm gonna try to compile this entire thing and maybe we'll try. There we go. So here's the actual address now. Look at that. Hopefully it's actually pretty small, but I know nothing about low-level development. Hello Gamoza, thank you so much for 21 months of tier 1 subscription. Thank you. Why is there a towel rack in the background? Are we in the bathroom? No. It's been there. I just renting this apartment and it's just like it's for the clothing. I think that's what it is. I never use that thing. I think I do from time to time. Yeah, but it is what it is. I can maybe put it away, but it's just been there. I'm too lazy to move it away. Right. So what do we have in here? Now finally we have an address. The curtain on the left, the towel rack at first glance made me think you were in the bathroom. Maybe I'm in the bathroom. Maybe it's gonna be the lower of this channel. I'm actually in the bathroom. It being low is accurate. I think most of the time when I get the entry point of my elves, it's somewhere. Oh, okay, that makes sense. All right. So let's continue. So here we're pushing this thing, and yeah, this is perfect now. This is perfect now. Right. What else do I want to have in here? I want to be able to have this kind of thing in here. Right, so I only implemented that for the constants, but I don't think I implemented that for like an actual compilation, right? I can get the address of the foo, I can cast it to integer, and then I can try to print it. But yeah, there we go. Okay, an expected word keyword address. Okay, that's cool. And I think when I do something like this, an expected keyword. Wait a second, it looks like we don't have a proper assert in here. Where am I? Why would it be like that? I'm not quite sure. Because in here, so if it's a token keyword, we'll just do that. And where are we? We are in a parse procedure, which is kind of sus, isn't it? I think it is. Because parse procedure is supposed to end at in, so I'm not quite sure what the hell is going on, but okay. So everything seems to be okay, but now, if I do something like this, then maybe, yeah, it should work. It should straight up work. An expected keyword address of. Oh, okay. So we probably have several places where we say unexpected keyword. I think I'm getting actually tired. And I'm not sure which one I'm talking about. I would presume I'm talking about the one that is compilation. Yeah, it's probably the compilation one. And the question is, okay, what the hell? I have a huge switch case for all of the keywords and I don't have an assert for that. What the hell? What the hell I was thinking about? Right, so I must have an assert. That's why I didn't catch that. Exhaustive handling of keywords in. And let me actually find something like proc. Proc. And I want to do something like that. In here. Count keywords. And how many keywords do we even have in there? We have 18 keywords right now. Right. So maybe even 17, but I'm gonna just add one in here. So the question is, which one do I want to add? Let me see. Let me see. So this is the keyword end, and somewhere here. So this is the keyword include. Where's the other keyword? I can always do something interesting in here, right? I can iterate like that. Yeah, that's way better. Okay, so this is the end, and in here what I have to do is keyword address of, right? And then we can say something like token. Token location, pointer plus, e puts, maybe here. To do address of is not implemented yet in compilation, right? In actual compilation. And then this thing is located here. And then we exit with non-zero exit code. Alright, so the result expression must be a single number. Oh, so this one has to be equals. Puts. Static type checking, how about that? There we go. So even though the amount of types in Porth is so small, literally 4 types, that static type checking catches so many errors, it's insane. Just a simple check makes the life so much easier. All right, so the rest of it not implemented for the compilation of our nation. Cool. And now I would like to just reuse whatever the code I wrote in const eval. Remember how I wrote like a lot of things related to parsing address of in const eval? I'd like to reuse all of that somehow. Const eval, eval, where is it? Eval const value, yeah. Address of. Really? What the fuck? Yeah, there we go. So I somehow would like to just like take that, put it in a procedure and just do something about it. Maybe I'm gonna have a procedure that takes Alexa, right? It takes Alexa and just does all of these checks. Maybe call it parse address of, and it will just literally return a value of that address, or fail if this thing is not present or something like that. We can work with that, I think. Proc. Okay, parse address of, and we're gonna accept a pointer which is gonna be the Alexa, right? So this is gonna be basically the Alexa, and what we're gonna get is an integer, right? And I suppose we're gonna expect this function to crash the compilation in case of any errors, right? So this is probably what we want to expect. Okay, and I'm gonna move this entire code in there. I'm gonna move this entire code in there. Proc, yeah. So this one is gonna be rather interesting. Just a second, I'm just checking everything. So, cool. So here we're taking the Alexa, right? We're taking the Alexa. We're also using some sort of a token. Let's allocate that token on the stack. Memory, token, size of token, right? So here's the size of token. So here's this thing on the stack. And we also have the Alexa, but I'm not sure if I want to have the Alexa also on the stack. Maybe I do want to have the Alexa on the stack. Working with the return stack is really, really painful. And I'm really looking forward to the stream where we're going to change that, right? I have a couple of cool ideas on how to make this kind of stuff a bit easier. Actually, I think significantly easier. We'll see how it goes. Okay. So here's that. Expected procedure. Okay. Parse, maybe let's call it after address of. So got that, and in here, right, we're gonna have something like this. So we have the token. So then we complain about that, and we need to simply return an address. So we can just do dupe, and here is an address that we want to return essentially. But it's kind of difficult to just return it like that because we have a couple of values here on top of the stack. So we have to be a little bit careful when we're going to be removing them. So I don't know. Maybe I'm going to just like allocate some sort of a result. Maybe not. I can try to get rid of this thing. This block. I can just go ahead and get rid of all of these blocks. Though it's gonna make it super inconvenient. One of the things we can do is just like swap drop. Whatever. Memory result size of integer. Right. And just like do it like that, right, and then just result integer. Easy clap. So shady language, my god. Okay, now can I reuse that function, right? So parse after address of, right, and const eval value address of. So essentially in here I should be able to just take the Lexa and the pointer and just parse this entire thing. So I don't have to have that, I don't have to have that, and I definitely don't have to have that. And I can just like move this stuff in here. This becomes sort of like this, right? This becomes like this. So parse after address of. There we go. So that's actually cool. Reusable code, by the way. Reusable code. And in here I can do a similar thing, right? So here is the Lexa. Where do I have Alexa? Lexa parse after address of, and here is an integer, and I can do op push address. Then I provide the address of this thing, then I say the token. Oh shit, fuck. So the token is going to be actually the previous token, but it's not going to be the current token. Fuck. Oh boy. Which is probably fine for now. It's not going to be super critical. I didn't think so, but to do. The token is refers to address of keyword, but not the name of the procedure, the address of which we are taking. I'm not sure if that's a problem, right? Because yeah, it's just gonna point to a different, like to the keyword. So I'm gonna just put it to do to think about that a little bit more, but like I'm really not sure if that's the problem. Okay, so would you look at that? So we implemented this kind of stuff, right? So we directly take the address of the procedure and we just print in it. We can also try to take the address of bar and also print in it. So here are two different procedures, and we can probably calculate like the size between them, right? So the amount of bytes and whatnot, 64 bytes. So a single like full procedure is actually 64 bytes in x86 64, which is too much in my opinion, right? But this is because port generates a pretty shitty assembly. But yeah, so address of actually works. So yeah, that's cool. And it even works in the compile time context, which is super nice. So, but that is only the beginning. That is like a half of the feature. The second half is actually calling that address. Second half actually calling that. Okay, let's go ahead and try to do that. It's gonna be interesting. Okay. Implement address of keyword. Right. So, okay, we introduced the type address. We introduced the keyword address of. The last keyword we need to introduce the keyword call like. Right. This one. We're gonna do something like call like foo, and like with any keyword, the first thing we're gonna do, we're gonna add support for the editor, right? So we want to be able to like see where we use this kind of keyword. Yet again, I'm gonna start with Emacs address of, and this one is gonna be something like call like. So this is for Emacs. Address of call like, and this is for Vim, right? We're gonna add support for both of them. And let me update the Emacs one. Emacs localhost, and I'm gonna just like copy paste this entire stuff in here. Let me restart the entire stuff. Cool. I don't remember if I addressed Anger Floof subscription. Thank you so much, Anger Floof, for tier 1 subscription. Your first subscription, by the way. I'm sorry if I didn't notice it 23 minutes ago. Pound Theory, thank you so much for tier 1 subscription for 7 months. Thank you, and welcome to our Epic Port Club. Thank you everyone for the subscriptions. I'm sorry if I'm missing them from time to time. Okay, So if I open foo port, there we go. Now we have call like, right? We have address of and call like. Cool. So we're slowly approaching COBOL in terms of the amount of keywords. So I think the thing about keywords is that the more keywords you have, the less words you can use as the names of the procedures and the variables. Maybe in the future we're going to replace some of these keywords with like maybe special characters or something like that. And yeah, I don't know. Alrighty, so let's go ahead and just like literally introduce a new keyword the way we usually introduce keywords, right? So we already have like a developed path of adding more keywords. So this is address of, and this one is call like. Okay, and that should fail the compilation. Porth, compile porth.porth, and I'm gonna run this entire thing, and I'm gonna compile foo.porth, and I'm also gonna run it. Right, there we go. Assertion has failed. Let me find this thing, address of, and call like. This one is rather interesting because this is a pretty long keyword, so we want to align that stuff slightly differently, like so, I think. It's a very nice alignment, I think. Oh, that was weird. I don't know what the hell has happened, but this is supposed to be address of. Let me take a look at the diff. Okay, so we just added that. Alright, cool. Seems fine. Call like. Call like. What kind of programming language is this? This language is called Porth. You can check it out in here. Just a second. Yeah. The cool thing about this language is that it's written in itself. What I'm doing right now, I'm developing, I'm editing a file called porth.porth. Right, so it's an implementation of this language written in itself, literally. So, and then what you can do, you can compile this thing down to an actual native executable, elf executable, and give its own source code to that executable, and it will be able to generate itself. Right. So it's a sequence of assembly instructions that, given the description of itself, can generate itself. So it's a self-hosted compiler. Right. So that's what we're developing in here. And on top of that, it's a stack-based language. If you never heard about stack-based languages, I recommend to Google it up, actually. Just stack-based. Stack-oriented programming. Wow, seems like Bash with the procedural style. I'm not sure if the syntax is the most interesting part of this language, to be fair. Borsche, thank you so much for tier 1 subscription, your first subscription, by the way, and welcome to Epic Porth Club. Is a self-hosted compiler compiling itself equine? To be fair, I was thinking about that, and I feel like that Quine is probably the simplest self-hosted compiler. Right, because implementing self-hosted compiler does feel like implementing a Quine. I can even show you something. There is a code in porth.porth, specifically a Lexa, right? So Lexa next, I suppose next token. This one is really interesting because this code implements string literal escaping, right? So let me actually find that. I wonder where it is. God damn, not really here. Here it is. Look, so here we're like sort of iterating through the string, and if we encounter like a backslash, we look at the next character after the backslash, and if it's n, we're interpreting it as /n. If it's slash, we're interpreting it as slash, you know, as actual slash, and so on and so forth. Look at this piece of code very, very carefully, right? This piece of code is using functionality that it's implementing. This is like a really fascinating piece of code. Like, and from time to time, I just go back to it and look at it and think about it. It's just like so fucking cool. It's literally like wine, right? Because yeah, it's implementing the functionality that it's using, because later the compiled version will go over this code and use this code to interpret its own interpretation. It's just like so fucking cool. And it's just like trying to implement at least once your own bootstrap compiler is just like worth it. Just to discover this kind of stuff. It's so fucking cool. I love it. I love it so much I'm forgetting how to speak English. Anyways. Okay. So we have something like this, and let's go to the next one. So this is a val const, and do I want to be able to use call like in a const evaluation? Probably not. I don't think it makes sense there yet. I do plan to actually have like full compile time evaluation, like being able to evaluate anything at compile time, but that requires a little bit of work. That requires a little bit, like a tiny bit of work, so we cannot do that yet. Okay, next one. So compile files, so address of, and if I encounter something like call like, keyword call. Oh, and this one is interesting. I think we'll need to introduce an operation call like. Yeah. So keyword translates to a specific operation. So let's go ahead and try to do that. So it's going to be op call like, and the value that we're going to be using here is going to be the address of the instruction that we're trying to call. Okay. So let's actually put something like this. Here to do compiling keyword call like is not implemented yet. Eputs, and I'm gonna exit with non-zero exit code. So parse after address of, and I want to have a similar thing. I want to have something like parse after call like, and it's also going to accept the lexer, and it's going to return the address of the instruction, right? That we're going to be using for the, it's not really address of the instruction, it's rather the index of the instruction that we're going to be using for the type checking. So, and in here, I suppose the parsing is going to be kind of similar to parse after address of, which means that I can probably copy paste this entire thing and just like adapt to a different thing in here. So let's see. So lexer, we take the lexer, expected procedure name after keyword call like, right? So this is going to be call like. But got nothing. All right. Expected token word human singular after keyword call like, right? But got this thing. So we can even probably extract this entire thing, this entire pattern into a different procedure, like parse word after. And maybe the specific kind of a token also going to be customizable, but I don't think we have too many cases for this thing to be abstractable easily. I don't know. All right, so in here, we just take this stuff, but here we take in the address, right? So here we take in the address, but I don't care about the address. I care about the index. All right. So here is the pointer to the proc structure definition, right? And I can probably put something like procs in here, which is the beginning of the array. And I can do the following thing. I can find the difference between these two pointers, right? So this is the pointer to the current thing, and this is the pointer to the beginning. I take the difference between them and I know the size of this thing in bytes, and I can now divide this entire thing by the size of the procedure and get the index in the procedure array, and I can save that to the result, I suppose. Right, so cool. So that's the difference in here. So certainly these two procedures, like these two things, like parse after call like and parse after address of, could be compressed somehow. They could be probably compressed somehow, but I just don't want to bother to do it right now. Maybe later. All right. So what do we have in here? I suppose I forgot to update this thing. Right. All right. Ah, shit. It's using NASM. FASM Linux x86-64. Alright, compile keyword like is not implemented. Okay, this is precisely what I was talking about. Okay, so I'm gonna do Lexa parse after call like, and that will give me the index to the, you know, in the procedure array. So next thing we're gonna do OP actually call like, right? Then we're gonna use the token. And it suffers from the same thing. It kind of suffers from the same thing. Call like. They're kind of similar. These two keywords are kind of similar. Yeah, all this structurally. Push OP. There we go. And we have an unknown operation. So this is the operation that we'll have to introduce. OP call like. Const OP call like. And this is where the actual functionality is going to get implemented. It's going to get implemented. It's going to... I don't speak English, I'm sorry. Alright, so this is that. Call like. Though, yeah, it needs to be call like. Generating. Okay. Do we have address of? Oh, there's no such thing as address of in here, so it doesn't matter. Okay. Dupe OP type pointer plus 64 OP call like if. And this one is going to be very, very interesting. So essentially, I'm popping this thing into the racks. So at the top of the stack, we have the address to the, you know, to the procedure. And now we just have to call it. Right, and the question is how we're going to call it? Probably the same way we just call things. We have OP call, right? And this is how we call things. So I'm going to put it in here and maybe even separate this like that. All right, so... Oh, shit. Oh, fuck. Okay. So Rax is usually used for this kind of thing, to prepare for the call, I suppose. I guess we can do that. But first we need to pop it into RBX. Okay, so in RBX we're gonna store this entire thing. Then we prepare the return stack, right? We prepare the return stack. Though this one, yeah. So this is the call. Then I prepare the return stack. After that, I probably have to call RBX, and I have no idea if it's gonna work because I don't know x86-64, so don't judge me. We'll see if it works or not. We'll see, we'll see. So we have that, and then we perform the call, and then I restore the original stack. And I think this is how we can do that. Right, so we take the address, we prepare this entire thing, we just call this entire thing, and then we prepare the stack back. So this could be the way to go. We'll see how it goes. So the assembly that we're generating is absolutely horrible, right? But I have a couple of ideas on how to generate a little bit better assembly. Right. So static assertion, 19, now we have 20. Okay, so what's that? This is type checking, isn't it? Yes, this is type checking. No, where are you actually? Exhaustive. Okay, so here, this is the compilation. Didn't I handle all of that already in here? I feel like I did. I'm really not sure why do I have this assert in here, so I'm gonna just like put 20. So now we have a type checking. Okay, cool. Address of OP call. OP call. So we take the token stack, procedure lookup by address. Okay, that's cool. And then we check if that procedure exists or not, or something like that. And then we did just type check. All right, cool. So let's go ahead and do that. P type pointer plus integer op call like equal if. All right. So then I get the token, right? I get the current state of the type stack. And now I'm taking the operand, right? I'm taking the operand. And I need to use this operand as an index within the procedure array. So I need to multiply this thing by the size of the procedure structure. And then I need to take procs and add this entire thing to the procs. So, and that gives me the pointer to that specific proc structure, right? So on this one, yeah. So here we check if that procedure exists in there, but I'm not sure if I want to do that. Maybe I'm going to put it to do, because I don't want to do it right now. To do check if the index to the procedure valid, right? So we're going to put it to do in here. Then I suppose I'm extracting the ins and outs of the procedure, of the current procedure in here. And then I perform the type check, right? I'm type checking it as the procedure that I provided in there. Then I increment the IP, and then I continue the loop. So let's continue the entire stuff in here. Okay, so I need to update. We're almost there, by the way, I think. I'm pretty sure we're almost there. I'm pretty sure about that. And not enough arguments for the call like I expected 2, but got 1. Why would you expect 2? Oh, I see. That makes sense. That means it works as expected. Look at that. Okay, so that means we have to provide something like 69 for 20, and then it will complain that we don't handle this kind of stuff, so we have to provide 69 for 20 and drop. Okay. And okay, unhandled data on the stack. And what's that data? I'm not sure what you're talking about. So integer comes from here, but this thing literally oh shit. Oh fuck. Oh shit, fuck. Actually, call like is supposed to expect. Huh. It is supposed to expect also the address. Yeah, I see. This entire thing just expects that plus also address. So because it's also consuming the address. Should be relatively straightforward to implement, I think. Relatively easy. All right. A p call like. So here is the ins, right? Here is the ins. And I'm thinking that I'm gonna just like extract this entire thing to a separate procedure. I think I should do that. Let me find other extracted things. I didn't see them. Yeah, so type checks. Yeah, so something like this. I think I should do that. Yeah. Something like type check call like. because I'll need to like put some stuff on the return stack. Hello, BXXL. Hi. Wait, so you wrote this entire thing in assembly? Not really. I didn't write this entire thing in assembly. Right, so what I did is actually I wrote a Python script that accepts Porth code and generates assembly. Right. So this is what I did. I wrote this thing. It accepts code in this and returns code in this. So from assembly, I can turn it into an executable, right? Then what I did, I implemented, like having this tool, like tool chain, I implemented porth.porth that can accept also porth files and generate this kind of stuff, like so. Probably want to do it like so. So yeah, and once I got this thing working, I got rid of the Python completely. And now I have a thing that is written in itself and constantly generate assembly. And what's funny is that I never really programmed directly in assembly, except for very small pieces, right? So I generate assembly, but I generate assembly like in very small like pieces in here. So I never wrote the whole program in assembly. Right, I just like small pieces here and there, and then I just like let the program generate the full program, if that makes any sense. So yeah, something like that. But I didn't program the entire thing in assembly because it would be too much work to do it like that. Because it's a rather complex program. Implementing something like that entirely in assembly is kind of difficult. I'm not gonna lie. Cheers, by the way. So what I want you to do, I need to abstract away the process of type checking of call like. I need to abstract it away. So let me see. Proc type check program from call like. So in here we probably need a stack and a current operator. Type check binary. So we usually take the token and a stack. So maybe this is precisely what we want. Type check CMP int operator. Type check something else, and let's go ahead and introduce that. Type check call like. So we're gonna accept the token that we're currently type checking and the current state of the stack, right? So, and that's basically what we need in here. Then call like. So this is the type checking that we're doing. So this is the token, this is the stack, and type check call like. This is where we're gonna do all of that. So this is the token, this is the operand. Well, I'm really not sure. I think we have to accept the operand in here. Right, so not the token, but the whole operand. Yeah, so let's actually provide OP. I think that makes more sense. So here's the whole OP, and I can just take the current stack. Memory stack, size of pointer. Step PTR, and when it comes to OP, I think I'm gonna also accept it by the pointer. OP pointer. So here's OP, I take that, I take the token, then I take the stack, then I take this thing, so it gives me the operand, I find this entire thing. And this one is very, very much interesting, because now this is the procedure that we've got, right? This is the procedure that we've got. And I want to be able to modify that thing quite easily, so I'm going to introduce proc size of PTR, and this is where I'm going to save this entire stuff, right? So we've got that, and I just save that into a proc, right? Then Well, not really. I think I'm gonna just do it like that. So what I want to do, I want to have ins, memory ins. Yeah, I just have the type stack. And outs, probably only outs. Not 100% sure. Yeah, maybe it's fine. So I'm gonna just like move it like this. All right, so we've got this. So this is the procedure. And then I drop this entire thing. So I dupe this stuff. Here is the ins. And in fact, I want to do size of type stack. Then I do over, take the ints, and I want to copy it into here. So it's going to be mem copy. And then I drop this entire thing. And then we do a similar thing for outs. There we go. All right, so we access the, yeah, that's what we do. So this is the operand. Then we read this entire thing. Multiply that, do that. And then we save it into a proc. We don't really need to save it into a proc, but yeah, this basically gives us the pointer to the specific proc thing, which we then extract the ins and outs. All right, we have ins and outs. For the ins, I want to actually push yet another thing in there. I think that's quite important. So what I'm going to push in there? Type stack push. Right, so let me quickly do that. The type that we're pushing in there is going to be data type address. The location is going to be in location from the operand, right? So this is the operand op token pointer plus, then token location pointer plus. This is the location. And then we have to provide the stack, and it's going to be ins, right? And after that, I just type stack push. There we go. So now I have a type stack that is the type stack of the original function plus the address of the procedure. So this is ins. And after that, I can finally type check this entire stuff. So let's see how we can do that. So type check stack. So I have to provide the token. Here is the token. I have to provide the stack. Then I have to provide the ins, outs, and then finally type check the entire thing. Cool. So that's the whole process. It's a little bit involved, but that should be fine. That should be fine. Right, so we take in the procedure, we extracting its ins and outs, and into the ins we push in yet another value, which is the address, right? And then we type check this thing as usual. We type check this thing as usual. So let me try to recompile the entire thing and see if it still works. Okay, so I probably didn't call this thing yet. I think I'm pretty sure I called it, didn't I? I'm pretty sure I did. All right, so isn't type stack supposed? Yeah, it's supposed to do that, but it just like didn't do what I asked it to do. So call like x expected to be address but got integer. So okay, that makes sense. Yeah. So what if we don't cast this stuff into an integer? Right. So there we go. So address of foo and call like foo and then drop. All right, that's cool. And did it do anything? It actually didn't do anything. Cool. It actually didn't do anything. That is very poggers, my friends. Absolutely poggers. I wonder why it didn't even work. So one of the things we can try to do, essentially, we can get rid of the of this entire stuff and just use 69, maybe like 1 print for the foo and 2 print. So not using the standard library is just like will produce a smaller executable. Right, and I would expect to see print 1 and 2. Right, but it didn't print anything. It, in fact... Oh, it's segfaults. Nice. That is actually very cool. It's straight up segfaults. I wonder why. Probably because you can't call from RBX. So let's actually Google up. x86-64 call from register. What register preserved through... call function pointer. How do you call a function through a function pointer past blah blah blah? Allocate the register, then call. Oh, you can just call without brackets, I think. I think we should try to call without brackets. Call like... Yeah, what if we just call RBX? Success! Easy. Easy clap. Ooh. Hell yeah. 2 hours. Precisely 2 hours. Okay, let's actually include the standard library, std port, and in here we're gonna have something like foo puts, right? And this one is gonna be bar puts. And if I try to run this entire thing, cool, it's foo bar. And here is the original example that we implemented at the beginning of the stream in C, right? So what I want to do, I want to have something like funcs, which is essentially size of address, right? We don't really have size of address, but we're going to implement that, n multiply by n, right? And we probably have to define a constant n, which is going to be, let's say, I don't know how many we want to have in there, like maybe 5, who knows? Right, so this is going to be something like that. And what I want to do, I want to take funcs and then 0 ptr plus, but it has to be also multiplied by size of address, right? Size of address multiplied by that plus plus pointer, and I'm gonna take address of foo, and I'm gonna save this entire thing in there, right? So, and this is gonna be foo bar foo. Cool. So we have 5 of them, right? We have 5 of them. And what I want to be able to do now, I want to be able to iterate through all of them. So while dupe less than n, right? So I just do funcs. Maybe I'm going to duplicate the index multiplied by the size of address. Then I'm going to take the funcs plus pointer, and here is the thing, right? And I want to read it as an address, and then I want to call it like foo, right? And then I'm going to increment this entire thing. Something like that. Some of these words don't exist yet. We'll have to add them to the standard library, but that's roughly what I want you to have in here. So this one has to be something like, yeah, 1, 2, 3, 4. Right, so let's take a look. Okay, and supported word size of address. This one is easy to implement. Const size of address is basically size of integer right now. Doesn't really matter. Now we'll have to do something like inline procedure at address. So essentially it will take a pointer and return an address. So I would say that it's an integer, right? But also we cast this entire thing to address. So that's what it is. So an inline proc address takes an address and a pointer and returns nothing, right? And in here we have this one is just, so we have to sort of like swap cast integer, then swap, and then just use a regular integer, right? And that should probably work. Yeah, probably. We'll see. Not enough arguments for call like. Oh yeah, so because they accept like values and whatnot, so this one has to be Yeah, 69,420, and then we're gonna do drop, right? So because this entire thing accepts 2 arguments and returns 1, in reality it doesn't really do anything. It's just like, yeah, just dummy stuff. And let me see, and it unhandled data on the stack. We forgot to drop the index. Okay. And it didn't work. I'm so happy. It literally did not work. I wonder why. Okay, so... So probably made a mistake somewhere in here, but I'm not 100% sure. So at address, I just take the pointer and I read this entire thing and I just simply cast it to the address. So that's fine. So then I take an address, I swap this thing, then I cast it to integers, then swap it back, and then I store it as an address. I don't see any problems in here either. So really strange, not gonna lie. Really strange. So let me try to do the following thing. So if I call foo 69,420 drop, it does produce foo, which is fine. Address of foo, call like foo. It's fine. Then I can take funcs and I can try to read it as an address, the first one, right? So should be fine. And it is in fact foo. It is in fact foo. Oh, I see what's going on. So basically 69,420 obscures this entire thing. Fuck, this is actually very not convenient. But I mean, if I implement the way I want you to handle the return stack, I think it's not going to be a problem. Okay, so for now, I'm going to just like get rid of the signatures in here. Right, so we're not going to have any signatures, essentially. But I get the idea. Okay. Look at that. Yes, so now we can have a polymorphism. So essentially now we can store an address to the function in an array, and we can quickly look it up and just call it, which will enable us with compressing huge if-elses, especially in the generation, right? So we have a generator, and depending on the current instruction, we just call different, we will call different procedures, and looking up that procedure is going to be O of 1 now, so we won't have to like do this kind of stuff. Hopefully this kind of stuff will be a little bit faster, right? All right, so the syntax kind of sucks, but it is what it is, right? Hopefully it's temporary, hopefully, not sure, but we'll see. But that's the thing we have. Not the thing we deserve. We definitely do not deserve this kind of shit, but that's the thing we need and have. So I'm gonna move this stuff into the standard library, right? Because now we have a new type in here. So this is gonna be std. And let me see. Right, so we even have this kind of stuff. So this is the size of the address. Might as well just, for the consistency, do it like that. So here is the getters for the types, and here is the setters for the types, right? So that's what we have in here. Look at that. For different types and shit. Wait a second. So this intrinsic doesn't care about this specific type, right? Oh yeah, I forgot that this intrinsic is actually, how is it called? Generic. Yeah, so I can just like do I64. Not I64, but yeah. I completely forgot about that. That's actually super cool. Yeah, so it's just like, it's completely generic. And now, if I try to do this kind of stuff. Oh, right, that's cool. So now, let me take foo and copy paste it to the tests super quick. Foo, and how am I gonna call that? Polymorphism, sort of. And let's do the tests. I'm gonna update output tests tests polymorphism. There we go. And if I take a look, this thing. So this is the expected, oh, unexpected keyword address. Oh, okay. Yeah, because it was using the old compiler to do that. It was using the old compiler. So what I need to do in here, I need to recompile the whole thing, right? I need to just recompile the whole thing and just move output to porth, right? There we go. So then I can do update. And if we take a look at this thing, fuck, it didn't work. What the fuck? Am I going crazy? I think I do. So why am I running this entire stuff? Alright, so that means this thing, like the output at least, has to support this stuff. Am I an idiot? I think I am. I think I'm already tired, so I really apologize if I'm doing something really, really dumb. So tests polymorphism porth. Okay, so that seems to be working. And if I do test update output for this thing, right? Finally, okay, so that's the expected output. So let's actually run the full tests now and see if anything's breaking. Does anyone have any questions regarding what we've just implemented? We finally implemented the function pointers and everything broke. I'm so happy. That's very interesting. Actual. Oh, I see. Okay, one more time. I really need to fix the output file name. I really need to do that, otherwise it's just like... I just busted my compiler yet again. Fuck. What happens if you call some function with call like with the wrong signature? Guess. Try to guess what's gonna happen. Alright, so let me bootstrap it again. This is gonna be your homework. Try to, like, guess what's gonna happen if you use a wrong signature. Unknown type and it... Fuck! This is annoying. I can't compile the compiler because it doesn't... Okay. Fuck. This is very fucking annoying. Okay. Alright. And then I'm gonna move the output to porth. Right. Then I'm gonna try to recompile the porth with itself one more time. Right. But this time with enabled this thingy. Yeah, finally. The compiler deletes itself, yeah. Okay, can I finally test my compiler? I should be able to. Full. Nice. It's testing itself. Alright. So does anyone have any other questions? What was the problem with passing arguments to code-like functions? None. Literally none of the problem. Would be interesting to have a block statement that creates an anonymous... Oh, we got FP people here. Okay. It's only been 2 hours when we already got FP people in here. Okay, so what failed? Something failed in here. Main function was not provided, but isn't it literally what it is? Oh, procedure. Okay. Oh yeah, I remember that I actually... So this was actually broken like before my changes, I think. Update output. Alright. Okay. Test full. All right, so test seems to be nice. Some examples. All right, and now Euler problems. None of that should be broken, by the way, right? But I'm checking that just in case, because I didn't really modify existing features, I just only added more features. All right, so... implement call like keyword. I'm gonna push that right into the repo, and it would make sense to add a couple of words to the documentations, right? Procedure pointers, right? Something like that. So this one is TBD. No, this is not really what it is. All right, so I need to do something like that. Procedures, inline procedures. So it probably makes sense to actually put somewhere in here. Procedure pointers. Fourth. Oh, by the way, you know what's funny? Right now, since we don't remove inline procedures, you will be able to take a pointer to inline procedure and that will work. But instead of inlining that procedure, it will actually call it. And another interesting thing, so as MM2PL said, now we have an ability to have mutual recursion. So this one's going to be interesting. So I'm going to put TBD in here. Readme stop procedure pointers section. At some point I'm going to just go through these things and document them. So I just need to have like a sort of like a table of content, right? What's in the language, what I need to document. So yeah. So tests, polymorphism, cool. So this is basically what we implemented. So now you can just take an address of a particular procedure and push that address on the stack, and then call that procedure like you know, a particular procedure in here. So does anyone have any other on-topic questions? Now it's possible to create QSort in C fashion, I suppose. Does it work with inline procedures? I literally just said that. I literally just answered that question before you asked it. Yes, it works with inline procedures. All right, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you on the next session where we're gonna implement, probably, I don't know yet, but probably we're gonna implement a new way of handling the stack, but I can't promise that. We'll see, maybe we'll have to implement something first. All right, thanks everyone for watching. I love you.